let's do another advanced example. So for example, let's take the limit as x tends to pi over 2 of secant of x minus tangent of x, which is infinity minus infinity. Okay, this one is an indetermination, but is not covered by the cases in L'Hopital's rule. So we need to figure it out. Here, notice that the secant is very special in that it's 1 over the cosine of x, right? And the tangent is the sine of x divided by the cosine of x. If you think about it, writing the definition of these two functions is practically the only thing we can do. But then when we write it like this, we discover that we can actually write them with a common denominator. So this is 1 minus the sine of x divided by the cosine of x, right? And now this is 0 divided by 0. And this is an indetermination, but it's one that we can do using L'Hopital's rules. So take the derivative of the numerator, 1 minus the sine, which is minus the cosine, and take the derivative of the denominator, which is the derivative of the cosine is the sine. Okay? And when I take x as p tends to infinity, what was that? X tends to pi over 2, then this is 0 divided by negative 1, which is 0. All right. And we can, let's do one more. Let's do the limit as x tends to 0 of x divided by the arctangent of x. Pause the video now and do it before I do it. Okay, anyway, this is 0 divided by 0, so it's one of the indeterminations that we can handle with L'Hopital's rule. So we can take the derivative of the numerator, which is 1, divided by the derivative of the arctangent, which is 1 divided by 1 plus x squared. So this limit that looked so difficult turns out to be the limit as x to 0 equal to the limit as x tends to 0 of 1 plus x squared, which is equal to 1.